The two last major applications of derivatives would be those that allow us to talk about the elasticity of demand and related rates. So, and both of those ideas answer the question, how does one thing change? If one thing changes, how does that influence another thing? So, if the price changes, how does the demand change? And that's what we're going to take a look at here. So first, let's look at elasticity of demand. And so if we think about the word elastic stretches, and if you pull an elastic, it will stretch out, but its fibers become thinner. If you kind of let it shrink back, it becomes thicker. So just by letting something be pulled, it's going to change the shape and how it looks. And so when we talk about elasticity of demand, specifically in business and that type of thing, what we're really doing is looking at how, if the price changes, how will the demand change? This is all based on what's called a relative rate of change, which means in relation to one item, how does another item change? Let's go ahead and say that elasticity of demand is going to help us define that how does the change in price affect the demand. All right, so elasticity of demand is going to help us know how elastic the demand is. How will the demand change based on the change in price? Now, what do you think would affect it? So when would something be more elastic than not? That has to do with whether an item is a luxury or a necessity. Because a luxury item is more sensitive to the change in price. If the price of milk goes up, the price of milk goes up, we're not going to see a very large change in the demand because this item is a necessity item. And so I know, like when the price of milk went way up a few years ago, I said to my children, it's still important for you to drink milk, but let's not drink it like it's water. And so we might try to not buy 4 gallons of milk a week. We might try to buy 3 gallons of milk a week. But the demand is going to stay about the same. Versus if an iPod price went way up, the demand would probably go down because that is a luxury item. Though we might think we can't live without our iPod, we truly can, and so therefore we would probably not buy it if the iPod price went way up across the board. Now, realistically, this whole concept has been changing over the last few decades because what we thought 30 years ago was a luxury, we now might be convinced it's a necessity just because of our lifestyles. And so this paradigm is changing a little bit. The formula for elasticity, again, is based on percent of change. It is technically the percent of change of the demand over the percent of change of the price. And I encourage you to read through this in the textbooks so that you can see how this formula was developed. But the whole idea is if the price goes up 10%, what percent will the demand go up? And so the formula for this is negative P for price over Q, quantity or demand, times the dQ dP, which is the change in quantity in relation to the change in price. So that's a formula for finding E. And let's talk about what the results would look like. Your E value is going to be in relation to the number 1. So if E can either be less than 1, E can actually equal 1, and E could be greater than 1. Now, let's start with E equals 1. This is called a unit elasticity. And what that means is that for each percent of change of the price, you're going to get the exact percent of change of the demand. So if you have a 15% price increase, you're going to have a 15% demand change. Okay, so if you have a 15% price increase, you're going to have a 15% demand change. If you have an elasticity of less than 1, that means that there's going to be little change in demand based on the change in the price. So when the price goes up, the demand is going to drop very little. These are your necessities. So if, for example, my elasticity was 0.2, let's write that as a fraction. That would be 2/10. What that would say is if you had a 10% price increase, you would only have a 2% drop in demand. So remember or think about it that elasticity is an inverse relationship. If the price, and I'm going to write in this little box right here, if the price goes up, then if it's really elastic, the demand is going to go down. And likewise, if the price goes down, we should see something cause the demand to go up, the more elastic it is. Now what about if the elasticity is greater than 1? Then we're going to see greater change in the demand. And these are your luxury items. So if I have an elasticity of 3.5, what that says, again, it's easier if you make it a fraction. So 35 over 10. For each 10% price increase, you're going to see a 35% demand decrease. Okay, so that's what elasticity means and how you interpret it. Now I'm going to show you mathematically there's a little bit easier way because you don't always have a 10% price increase or 15% price increase. So how can we use the 0.2 and the 3.5 to figure out exactly what our increase will be? And so before we go into the example, let me just slip in an example in general that we don't have to find the formula for. So let me go ahead and give us the formula, and then I'm going to show you how to develop the formula. So what if we knew that E equals P over 20 minus P? And I'm going to show you in a minute where a formula like that comes from. Let us find three values, E of 4, E of 16, and E of 10, and interpret that. Well, first let's identify what these 4, 6, and 10 represent. This is E of P, so this is our price. So the question is here, if my current price is $4, what will happen to the demand if I raise that price by 10%, if I make it $4.40? Or what if I raise it by 50% and make it $6? So your elasticity depends on two things. What is your current price and what is your change in price? So for elasticity, two items. One, what is current price? and 2, what is percent of change. Okay, so those are going to be the two things that help us determine what's going to happen to the demand. All right, so let's find E of 4. We're going to simply plug 4 in. And when we do, we get 4 over 16. Now we could technically stop there, and what that says is for every 16% of change in the price, we're going to see a 4% change in the demand. But we talk about elasticity in terms of a decimal. And so we have 0.25, which is less than 1. And when it's less than 1, it is inelastic, which means we're talking about milk versus iPods, so it's a necessity. And so let's see what this says. If the current price is $4, we could say, what would happen if I raised my price 16%? Okay, we could talk about that percentage. We could talk about any percentage. But what if I just say, if I decide to, and I raise that price to $4.40, which is a 10% increase. So I'm going to raise the price of milk from $4 a gallon to $4.40, which is a 10% increase. Here's basically what we would have to do each time, is take 4 over 16 equals, we're not doing a 16% increase, we're doing a 10% increase. So you could do it that way, where you set up a proportion and you solve for x. Or another way to look at it is 4 over 16 is the same as 0.25 equals my demand change over my price change, and now I just multiply. So it would be x equals 0.25 times 10. And so that gives me a 2.5% change of demand. Okay, so if I raise my price, if my price goes up, my demand is only going to drop 2.5% of my current sales. Not a lot of change. And so if I'm really in it for the money, then as a businessman, I may take this chance, because my revenue, if I go up to $4.40, my revenue is going to increase because I'm going to charge more per item and people are still going to buy it. So that $4.40, that extra 40 cents, is going to increase my revenue because I'm not losing much sales. So in that case, it's a good thing for me to raise prices. Now, you might have a boycott on your hand, like what happened with the whole gas price thing a few years ago, where when the prices jumped in one day from $2.20 a gallon to 4 something, and so then the government stepped in and said, wait a minute, you're taking advantage here, you can't do that. And so sometimes it causes problems politically, but technically a person that's in it just for the money would make the decision to continue to raise prices. Now let's plug in 16. So when I plug in 16, I get 16 over 20 minus 16, which is 16 over 4. And this is just coincidence that the two numbers I picked are giving me inverse relationships. But, so what does that mean? Well, I could say that for every 4% increase in change, I get 16% drop in demand. Or I can say that my elasticity is 4, which is greater than 1, which means I'm going to see some effects on my sales, based on the price change. So if my current price is $16 and let's go with that 10% again. I raise the price 10%. Then my demand is going to change by a factor of 4. Again, we could use the ratios, and so my demand is going to drop 40%. So now my revenue is going to go in the opposite direction because I might get 10% more price. So now instead of $16, I'm getting $17.60, but I'm going to lose so many sales that I'm going to end up with a decrease in revenue. So this one resulted in an increase in revenue because even though my price went up, my demand did not drop. Here I'm going to get a decrease in revenue because my price going up even $1.60 is going to drop my sales 40%. And then the last one, E of 10, when I plug in 10, I get 10 over 10 or 1. So this is what is called unit elasticity, meaning that for each 10% increase, I'm going to see a 10% drop or a 10% decrease. So there's the same amount of change in demand as there is in price. So if I have the price is if the price is currently at $10 and I raise it 10%, so now it costs $11. Then my demand is going to decrease 10% as well. Okay. So that's how elasticity works once you get your formula. So now all we need to do is look at how do we get the formula, but this would be how you interpret it. So let's take a look at this example. We have that Q equals 100 P minus 17. Remember the formula for E is negative P over Q times dQ dP. Okay. Well, we know what P, well, we don't know what P is. P is our price, so we're doing this in terms of the price, so E of P. So we're going to leave that P alone. Q, we're going to plug in this, so 100P to the negative 17. And then we have to have our dQ dP. So we need to go back to that original function and find the derivative of it. So the derivative would be 100 times negative 17 P to the negative 18, or negative 1700 P to the negative 18. And so I plug that in here. And so what we're getting ready to do is talk about what's going to happen to the demand of heroin if the price increases. Okay, so what's going to happen to the demand of heroin? And so let's clean this up. And so let's get all the P's so they have positive values. So I'm going to move this up and put it with this one. So on top I have and I have a negative times a negative there, so I have 1700. On top I have P to the 18th, and I can move this guy down, P to the 18th, so I get that my demand is 1700 over 100, which is 17. So if my E is 17, I can put a 1 under it to make it a fraction, which would say if my price went up 1%, my demand is going to drop 17%. And so if we were to take So in this case, the current price is not as much the factor as just the increase in price. So for every 1% that our price increases, we would we would expect the demand on heroin to be a 17% drop. Now, I mean, I certainly don't know this from experience, but also the problem with heroin and what this formula doesn't recognize is that heroin is an addictive drug. And so what crime investigators and detectives do is they watch the street price of heroin, because here's what might happen when we have a drop in or an increase in price. The price of heroin goes up, which technically means the demand for heroin is going to drop about 17%. But it's an addictive drug. And so that 17% of the people, if their addiction level is too high, are not going to be willing to not buy their heroin. What does that do in the real world? That increases the crime rate, because now the price of heroin has gone up. We have 17% of the people that can't afford the price, but their demand is addictively still there. Now we start to see break-ins and robberies increase among addicts. And so, while it may not exactly tell us what, it tells us what the demand effect should be based on current trends, but sometimes when you have something enter like an addiction, now they start watching, they beef up the patrol in certain areas, because now they're going to start seeing robberies because the addicts need the money to meet the price increase because they have an addiction. So all this stuff that we look at doesn't stand in isolation. What it does is serve as indicators. And so people that work in detective work and police work regarding drug trafficking are going to watch these types of numbers. Now let's take a look at related rates. And related rates, again, is going to address in a different way how when one item changes, something else changes. So for example, what would happen if I was riding a bike and I started pedaling faster? Well, my speed would increase, my time would decrease, that it would take me to get somewhere. So I could talk about, if I pedal this much faster, how will it affect the change in my speed, or how will it affect the time it takes for me to get there? If I'm pouring liquid into a cup and I started pouring it faster, what does that change? It changes the height of the liquid in the container. It changes the volume in the container at a different rate, and we can talk about that. And if I'm running a marathon and then all of a sudden I start walking, then I have decreased my speed. That's going to increase my length of time. It's going to slow down my heart rate. So again, I can talk about how one affects the other. What if I increased my study time? What would that do? Well, we might look at, does it increase your grade? Does it decrease your grade? Does it increase your anxiety level? Does it decrease your anxiety level? So if we had a oil spill, for example, and the oil was spilling, as the radius changes, the area of this circle is changing. And depending on how fast or slow I let my radius grow is going to affect how fast or slow my area goes. So what we're getting ready to talk about is, so as my radius changes over time, what does that do to the change in my area over time? So notice now what we're doing is we're talking about things changing over time. And so we're going to write equations like the area of a circle equals pi r squared. And to talk about the change in those things, we're going to take the derivative of this area formula with respect to time. And that's why implicit differentiation comes in, because remember, when you take the derivative of something with respect to a different variable, like dy dx, you're going to have that dy dx. Okay, so we're talking about if one thing changes over time, how does the next thing change over time? So here's what we're going to do. Is first of all, we're going to write an equation that relates the variables involved. So in the case of that circle, our two variables were the area and the rate. Then we're going to differentiate that, or take the derivative in relation to time, so that we can talk about the rate of change over time of each one. Okay. So let's do this example. How fast is the radius of a spherical soap bubble? So I have a bubble and I start blowing it, and it has a radius. Okay, how fast will that radius change when you blow air into the bubble? All right, well, when we blow air into the bubble, we're talking about changing its volume. And so we need a formula that relates. So number one, we need to relate V and R. And then what we want to know is we want to know dr dt. We want to know how the rate of the radius is changing over time if we know what the volume is changing. So if I change the volume over time, how will my radius change over time? So first we need to start with our volume formula. And we know that the volume of a sphere is 4/3 pi r cubed. And if you don't know that, you need to look it up. So you may have formulas or relationships here you need to look up. Now we're going to take the derivative of both sides with relation to t. So we're going to take the derivative of this with relation to t, and we're going to take the derivative of this with relation to t. So on the left side we get dv dt, and remember that 4/3 pi is just those are just numbers, so those like a coefficient, times the derivative of r cubed would be 3r squared dr dt. 3r squared dr dt, because you have to take the derivative of r with respect to t, and that's not 1. Now we simply need to solve this for dr dt. So let's clean it up a little bit. We get dv dt. The 3's are going to cancel, and we're left with 4 pi r squared dr dt. And so now solve for dr dt. You could just plug into this whatever you know, or we can get dr dt by itself. So it would be divide both sides by 4 pi r squared, so I'm going to do 1 over 4 pi r squared times the change in volume is going to give us our change in the radius. Okay. And so what if we are increasing the volume at a rate of 10 centimeters cubed per second? We know that's a dv dt because centimeters cubed is volume, seconds is time. So if it's a rate of change in centimeters cubed per second, that's our dv dt. So we're going to plug in dv dt, which is 10. and that will give us our dr dt. And so really, you can clean that up a little bit. You get 10 over 4 pi r squared. You could clean that up, make it a fraction, but that's your dr dt. So there's still an r in here though, and so then the question is, so what is our change in radius? Well, the change in radius is going to be, so the 10 over 4 pi r squared, we could make that 5 over 2 pi r squared. That's going to give us the rate of change of our radius over time. But the balloon, or a bubble or a balloon, whichever one, when you first start blowing up a balloon, the radius grows pretty quickly. But as the balloon gets bigger and bigger and bigger, and you put more air in it, you see the balloon grow less and less. So if our radius is only 1 centimeter, if we plug 1 into this and work it all out, we get 0.8 centimeters per second. My radius, every time I put in 10 more cubic centimeters of air, we're going to see it growing 0.8 centimeters a second. Versus if I put r equals 10 and work it out, that's 0.008 centimeters per second. My radius is not going to grow very quickly at all. So again, reviewing the steps. Number 1, you have to determine what variables you have. Number 2, write an equation that relates those two variables. Take the derivative with respect to time, and then interpret. And typically, the change in 1 is going to depend on where you are in relation to, for example, in this case, where you are in the volume already, or where the radius already is. That's going to help you determine the change in volume. Let's look at a slightly different problem, and that is, how fast does the water level change or drop if it is drained at a rate of 3 liters per second? Now, liters is not typically a unit of volume. It is volume, but it's not a measurable, physically measurable unit of volume. We need to know that 1 liter equals 1,000 centimeters cubed. And so what that really is, 3 liters would be the same as 3,000 centimeters cubed per second. And we are draining something, so that rate of change is negative. So our change in volume over time is a negative 3,000 centimeters cubed per second. Okay, now we want to know what's going to happen to the height. So I need some formula that has V and H in it. So we have ourselves a tank. We've got a drain on it. Water's dripping, and the height of the water is changing. The radius of this is not changing. It's the height that's changing. So the radius is going to be a constant. So we're going to use the volume formula again, and this one is pi r squared h. Take the derivative of both sides with relation to t. Remember that pi r squared is not changing. That's a constant, so that's our coefficient, times dh dt. Now, before we solve for dh dt, but what I would get in the habit of doing is going ahead and plugging in things that we know for this problem. So we know that dv dt is negative 3,000, so we could plug that in. We weighted on the problem before. And so dh dt is negative 3,000 over pi r squared. Now remember, r is not changing because it's a constant, it's a tank. We're not changing the size of the tank. So as the water drains, the height is decreasing because we have a negative value here, because pi r squared is going to be positive, So dH dt is going to be negative, and so as the tank is draining, the water level's draining. And then you can plug in for R if I knew, for example, that I had a tank that was 50 centimeters across. I could plug in 50 and see the speed that the height would change. Because think about it, if you have a something that's real skinny, then it's going to change pretty quickly. But if the height is going to change pretty quickly. But if you have a tank that's a real big, wide tank, the water level is going to go down slower. Think about draining a rain gauge or a tube versus a pool. You don't see the water level in the pool change as much. Let's look at one more example. All right, so this is one on how we might model, as we look at this example, we are building a tower, and we want to know, is it worth adding height to our tower? So everybody knows that you can see a lot further from the top of a mountain or a high building, but how much further? So for each foot I go up, how much further can I see? Well, a model that has been developed that determines how far you can see based on how high you are is D equals 3.57 square root of h. So let's find the rate of change of the distance with respect to the height. Okay, the rate of change of the distance with respect to the height, meaning as the height changes, what does the distance change? Now I'm going to use this opportunity to do something just a little bit differently. We're going to take the derivative of these, and we're going to do this with respect to h, because in this case the time really doesn't matter. So while most of the time when we talk about change, we talk about it with change over time, but in this case we want to talk about the change in distance we can see in relation to height. So we're going to take the derivative of both sides with respect to height. So on the right we have the derivative of distance with respect to height, and now on the right side 3.57 is a constant. Remember, we can write this as 3.57 h to the 1/2. So we multiply it by a half and decrease that by 1. And the derivative of h with respect to h is just 1, so we won't have a dh over here. And so our final answer is 1.785 over the square root of h. So if I want to know when the distance will change, I need to know what height my tower already is. So I put in my current height of the tower, and I will plug in, and then this will tell me how much further, what's my change in distance. So let me go to the next screen and we'll actually do that. So if I know that the change in distance with respect to height is 1.785 over the square root of h, and my current height is 300 meters high, or I'm building a tower that's 300 meters. And so then they want to know what my increase would be. So my ddh, if I plug in 300 and I work that out, I get 0.103. And that is my change in distance with respect to height. So what does that mean? Well, I could technically put a 1 under it because I have dd over dh. So for every 1 meter I go up, I'm going to be able to see my change in distance is going to be 1.03 kilometers increase. Okay. Or I could have written that as 103 over 1,000, which says for every 1,000 meters that I go up, I can see 103 kilometers further. Okay, so you can either put it over 1 and talk about your change per 1 unit of increase, or you can write it as a fraction. All right. Now we've had quite a few oil spills. We had one in Alaska a long time ago. We've had one down in the Louisiana area more recently, and so this whole oil spill thing is quite something that we look at. And so let's look at, assuming that the slick is pretty circular, we want to write an expression for the growth of the oil spill. And we need to get a grasp on how fast this circle of oil is growing on the water so that we can control it. So based on how fast the volume of the oil is coming out of the well or out of the ship, what is that doing to the circle? So first, let's write an expression that relates radius with time. We're given that the area of this particular oil spill in relation to time is A equals 9t. That's a model that they did by collecting data. We also need to somehow get radius involved, and A equals 9t doesn't involve the radius. So, but if we start with A equals 9t, we know that area of a circle is pi r squared, so we can write a formula for r in relation or in terms of t. So we'll get r by itself and then take the square root. So the relationship between the radius and the time is square root of 9t over pi. And now we're concerned about how fast that radius is growing over time. Okay, so how it's growing over time. So we're going to take the derivative of that. So first I'm going to write this actually as a decimal. I'm going to do 9 divided by pi and take the square root. So that'd be 1.69 t to the 1/2. Now we're going to take the derivative of this with respect to t. And 1.69 times 1/2 is 0.85 t to the negative 1/2, and the derivative of t with respect to t is 1. So dr dt equals 0.85 over the square root of t. So I can put in today how many, if it's 16 days into the oil spill, I can plug in 16. And when I do, I get 0.21. The distance is in kilometers. Per time is days or day. So if this is day 16 of the oil spill, at the end of the next 24 hours, I can expect that oil spill to have grown 0.21 kilometers. So if I'm an environmental scientist, I better work on, getting this thing under control, because on the day 16, it is growing 1/5 of a kilometer. Day 17, will grow a little bit less. In other words, it will start to slow down a little bit, but it will continue to grow. So this is the idea of relating two things so that you can look at how one relates versus the other. Make sure to come up with an equation that relates the two variables. Take the derivative either in respect to time, if you're talking about how things are changing over time, or take the derivative of items as you with respect to one changing. For example, with respect to height. As the height goes up, what does that do to the distance the person could see on that tower? And then, most importantly, as you wrap up this this topic, is that you do work on making that connection. What does it really mean that drdt is 0.85 over the square root of t, and what can that help you with?